A structure along with the loads applied on it is shown in figure. Self weight of all the members is negligible and all the pin joints are frictionless. A is a single member that contains pin C. Likewise, B is a single member that contains pin D. Members GA and FJ are overlapping rigid members. The magnitude of the force carried by the member CI is dash kilonewton. Okay, structure given structure and the self weight of all the members is negligible. We are not considering the self weight, but here A and A and B are single member. Okay, one end is fixed. Here both A and B are single member, and both contain pin at C and D. And all we have to find is the magnitude of force carried or acting at the member CI. So first of all, we need to draw the forces acting on each member. So I will show you how the force acting in each member. So the second figure is drawing with all the forces acting on each member, and we are neglecting AE and frame A and B just because it is fixed at one end, so there won't be any tension on that frame, both AE and B, and the remaining CI, EI, EF, and IH and FG is drawn, and force 2 kilonewton is acting at the end of H, and 4 kilonewton downwards acting at point G. So there is a force of 2 kilonewton acting rightward along CH. So as we know, the direction of tension will be opposite to force. So that's what we do convention even in for a string loaded by a mass, right? The tension will be upwards, then weight will be downward. Just like that, 2 kilonewton is rightward and the tension will be leftward. Similarly, EI would have a tension, and similarly EF would have a tension away, but the 4 kilonewton won't have any effect. Like all the tension will be due to the 2 kilonewton mainly, just because it acts along the frame. So this is a diagram that shows all the force acting excluding the frame which do not have any tension. So next step is simply apply the law of static equilibrium. This whole frame has to be in equilibrium to be stay like that. Okay, first of all, first condition is the forces has to be in equilibrium, and second one is moment of inertia has to be zero. So the force has to be equilibrium, moment of inertia have to be zero. So here the best suitable case is to apply the moment 0. So I will be considering the point E. Just because I need to find CI, the most suitable point will be E. At point E will be the most suitable point. So the moment due to frame CI will be opposite direction compared to the remaining two, and that's why I put negative direction, because it's in anti-clockwise direction with respect to the point E. And that tension EI is along point E, so there won't be any moment of inertia due to tension EI. Similarly, there won't be any tension due to moment of inertia due to tension EF. Only forces which cause the moment of inertia is 2 kilonewton, 4 kilonewton, and tension CI, and CI will be on anti-clockwise direction, so minus TCI into 1.5, and 4 kilonewton is clockwise direction plus 4 into 6, and 2 kilonewton is also in positive direction clockwise direction plus 2 into that perpendicular distance 1.5, because this whole frame CH is half the distance of the total height 3 meter, that's why it's 1.5 meter. So from that we can find TCI, the tension. TCI tension acting along the frame CI is 80 kilonewton.